Imagine your entire city silently and inexplicably drifting across an unseen ocean. Now scale that up. In the 1970s, astronomers made a discovery that would change everything. Our entire Milky Way galaxy was already on the move, pulled by invisible forces. The question wasn't, are we moving, but where are we going? What is your address? Not merely the numbers of your dwelling, nor the name of your street, or even the sprawling city that hums with life. Where truly are you? From the quiet solitude of our homes, we often forget that our very planet is a tiny sphere, spinning, hurtling through a vast, indifferent void. This blue marble, our cradle of life, is bound to a star, a common yellow dwarf, which in turn orbits the heart of an immense stellar island. The Milky Way galaxy. For generations, we saw our galactic home as a steadfast beacon, a cosmic anchor in an otherwise dizzying cosmos. But in the twilight of the 1970s, as disco pulsed and space probes stretched their metallic limbs towards the outer planets, astronomers made a startling, unsettling discovery. The Milky Way was not stationary. It was not at rest. Our entire galactic neighbourhood, containing hundreds of billions of stars and countless worlds, was adrift, being pulled relentlessly by immense invisible forces toward a destination unknown. Imagine, if you will, a vast ocean stretching infinitely in every direction, and your home is a tiny raft upon its dark, moonless surface. The currents are subtle at first, imperceptible to the eye, yet they tug at your vessel, carrying you silently but surely towards an unseen horizon. This was the cosmic predicament of the Milky Way. Our galaxy, a breathtaking swirl of starlight and cosmic dust, was an active participant in a grand unseen celestial ballet, its every star and nebula contributing to a collective motion that defied the long-held assumption of a universe in static equilibrium. This wasn't merely a shift, a slight wobble, but a purposeful directional flow that hinted at gravitational giants lurking in the cosmic depths, forces powerful enough to command the movements of entire island universes. The revelation struck at the very core of our cosmic understanding, challenging the Copernican notion that we occupy no special place by showing us we are not truly at rest. It was the first inkling of a truth far grander and more dynamic than we had ever conceived. The universe is a fundamentally noisy place, and everything in it is in ceaseless motion. For centuries, humanity had charted its course by the fixed points in the heavens, from the patient progression of the planets to the seemingly eternal backdrop of the stars. Our understanding of our cosmic position had steadily expanded from an Earth-centered world to a sun-centered system and then to a galaxy-centered view. Each step brought a new scale of awe and humility, but this new discovery, born from the subtle whispers of distant light and the tireless work of unseen observatories, peeled back another layer of cosmic illusion. Our entire galactic home, this majestic island of light, was revealed to be a participant in a larger unseen river of gravity. It wasn't just our sun, or our planet, or even our local group of stars that moved. It was the whole vast collection, hundreds of billions of solar systems, trillions upon trillions of kilometers across, collectively streaming towards an unknown gravitational well. The initial problem was profound. How could such a titanic motion be measured when its very immensity rendered it imperceptible to our local instruments? And what silent, powerful architect was orchestrating this colossal drift? The universe, it seemed, was preparing to reveal a deeper, more profound level of its endless, restless dance. But how could such a monumental drift involving our entire galaxy have remained hidden for so long? The revelation of the Milky Way's movement, as established in the preceding chapter, hinted at unseen gravitational architects, yet their presence was shrouded in mystery. The answer lies in one of the most frustrating and fascinating features of our cosmic neighbourhood, the zone of avoidance. Picture yourself standing at the very heart of a dense, swirling fog. The light from distant lamps is scattered, absorbed, rendered invisible by the thick mist surrounding you. So it is with the Milky Way. Our galaxy, a majestic spiral, is teeming with gas and dust, particularly in its plane. These cosmic clouds, beautiful as they are, act as an impenetrable veil, obscuring our view of the universe beyond. It is an astronomical blind spot, a vast swath of the sky where the very stuff of our galactic home prevents us from seeing what lies behind it. For decades, this zone of avoidance presented an insurmountable barrier to mapping the full extent of the universe's large-scale structure. It was like trying to understand the full sweep of a vast mountain range when a dense forest perpetually blocks your view of the most crucial valleys and peaks. Any motion we detected in our galactic vicinity could be attributed to local effects, to the intricate dance of nearby stars or the majestic swirl of our own spiral arms. The notion of a grand overarching flow pulling thousands of galaxies remained a speculative whisper, unable to pierce through the dense cosmic fog. This obscured region became the unwitting accomplice in hiding the true nature of our galaxy's journey, leaving humanity's cosmic position akin to that tiny raft adrift in a moonless ocean, unaware of the powerful currents beneath its hull. The zone of avoidance was not just a blank spot on the map. It was a profound mystery, a challenge to our very perception of cosmic reality, whispering of hidden truths just beyond our sight. Astronomers for generations observed the heavens meticulously, charting the positions and movements of stars and galaxies. Yet there was always that curious gap, that band across the sky, where the visible universe seemed to fall silent. This silence was not due to an absence of galaxies, but a profound overabundance of our own galactic material. Our Milky Way is a barred spiral galaxy, a colossal disk of stars, gas and dust spanning over 100,000 light-years. When we look along the plane of this disk, we are staring directly through vast quantities of interstellar medium. This medium, composed of hydrogen and helium gas along with microscopic dust grains, efficiently absorbs and scatters visible light. It's like trying to see through a dense wall of smoke. This absorption, known as extinction, is particularly strong in the optical and ultraviolet wavelengths, effectively rendering large sections of the sky opaque to our traditional telescopes. While individual stars within our galaxy are visible in these regions, the faint light from distant galaxies is almost entirely extinguished. This created a profound observational bias, leading early astronomers to underestimate the true homogeneity of the universe's distribution of galaxies. It was a classic problem of observational astronomy. What you don't see, you can't account for. And what we weren't seeing was potentially the very force orchestrating our galactic drift. The zone of avoidance was a cosmic curtain behind which lay the greatest gravitational secret of our local universe. Its very existence meant that any full understanding of our galactic movements and the forces driving them would require instruments and ingenuity capable of piercing this obscuring veil, hinting at the deeper problems that would challenge a new generation of cosmic cartographers. To pierce this veil, to map the unseen currents of the cosmos that pulled our Milky Way into a vast, unsettling drift, and to see beyond the obscuring zone of avoidance required not just new instruments, but a new way of thinking. It demanded pioneers willing to listen to the whispers of distant galaxies rather than just observe their static forms. In the late 1970s, two such pioneers emerged. Brent Tully and Richard Fisher. These astronomers, working with a profound sense of purpose, understood that if the Milky Way was truly in motion, then its galactic neighbours must share that flow, hinting at a grander cosmic current. Using the formidable Parkes radio telescope, a monumental dish, listening to the faint radio emissions from across the cosmos, they embarked on a groundbreaking quest. Their approach was ingenious. They weren't just looking at galaxies. They were listening to them, measuring their peculiar velocities, the subtle shifts in their spectral lines that revealed their motion towards or away from us. This technique, known as the Doppler effect, is a fundamental principle in astrophysics. Just as the pitch of a siren changes as it moves towards or away from you, the wavelength of light or radio waves emitted by a galaxy shifts depending on its motion. If a galaxy is moving towards us, its light is blue shifted to shorter wavelengths. If it's moving away, it's red shifted to longer wavelengths. By precisely measuring these shifts, Tully and Fisher could deduce the velocity of each galaxy along our line of sight. Their work was a painstaking act of cosmic cartography. Each distant galaxy was a single data point, a tiny clue in a grand unfolding mystery. They focused on the 21 centimeter line, a specific radio emission produced by neutral hydrogen atoms, which are abundant in spiral galaxies like our own. This particular wavelength is crucial because it can penetrate the dust and gas of the zone of avoidance, offering a window into the otherwise hidden universe. By meticulously mapping the velocities of thousands of galaxies spread across vast swathes of the sky, they began to discern a pattern, a common direction, in which these island universes were streaming. It was like watching thousands of individual leaves caught in a vast unseen river, all flowing in the same general direction, revealing the presence of an underlying current. This wasn't the uniform expansion of the universe, but an additional localized drift, a gravitational tug-of-war on a scale previously unimagined. Their early results were compelling, hinting at a large-scale structure, an unseen gravitational anomaly, pulling not just our Milky Way, but an entire cosmic collection of neighbouring galaxies into its relentless grasp. This was a pivotal moment in observational cosmology. Tully and Fischer had begun to peel back the first layers of the zone of avoidance, not by looking through it, but by observing the effects of what lay beyond, giving humanity its first true inkling of the cosmic currents that shaped its journey. They proved that the unsettling drift was real and widespread, setting the stage for the identification of the enormous gravitational anomaly that was causing it. Their pioneering work not only confirmed the dynamic nature of our galactic neighbourhood, but also laid the methodological groundwork for future, even more ambitious surveys of large-scale cosmic flows. Their detailed measurements were a crucial step in transforming a vague suspicion into a quantifiable scientific problem, demanding a deeper understanding of the universe's true architecture. While Tully and Fischer meticulously measured the individual motions of galaxies, charting the unsettling drift that stirred our cosmic neighbourhood, another even more fundamental cosmic signature was revealing the universe's overall motion. This signal came from the very dawn of creation, from the afterglow of the Big Bang itself. The cosmic microwave background, or CMB, this omnipresent radiation, a uniform bath of ancient light permeating the entire cosmos, is the cooled remnant of the universe when it was a mere 380,000 years old, a time when it finally became transparent to light, releasing its trapped photons. On a grand scale, the CMB is almost perfectly uniform, a testament to the remarkable smoothness and homogeneity of the early universe. Yet almost is the key. Subtle variations exist, tiny ripples in the fabric of this primordial light. These are the faint imprints of the initial quantum fluctuations that eventually grew into the large-scale structures we see today. But within these ripples, scientists discovered a profound temperature bias. The CMB appeared infinitesimally hotter in one direction of the sky, and infinitesimally cooler in the exact opposite direction. This wasn't a feature of the early universe. It was a Doppler shift, a cosmic echo of our own motion through this ancient sea of radiation. Just as an ambulance siren sounds higher pitched as it approaches and lower as it recedes, our motion relative to the CMB causes the light waves to be slightly compressed in the direction of our travel, making them appear hotter, blue shifted and slightly stretched in the opposite direction, making them appear cooler, red shifted. The magnitude of this temperature difference is astonishingly precise, a mere 0.35 Kelvin hotter in the direction of the constellation Leo and cooler towards Aquarius. This seemingly tiny deviation, first definitively detected by the COBE satellite in the early 1990s, translates to a colossal speed. It indicated that our solar system, and thus our Milky Way galaxy, is moving at approximately 600 kilometers per second. Relative to this universal reference frame, the cosmic background radiation, this speed represents our absolute velocity through the universe. However, this raw 600 km measurement is a composite. It includes the Earth's orbit around the Sun, the Sun's majestic dance around the galactic core, and the Milky Way's own independent motion. To isolate the galaxy's true drift, we needed to subtract these smaller known movements. Even after accounting for the Earth's orbital speed of 30 km and the Sun's roughly 230 km journey around the galactic centre, a substantial residual velocity persisted. This colossal speed, pointing unequivocally towards a mysterious unseen attractor, was a stark confirmation that our journey through the cosmos was far more dynamic than we had ever dared to imagine. The CMB, the very first light of the universe, was whispering the truth of our galactic drift, providing an independent fundamental piece of evidence that perfectly complemented the direct galactic measurements of Tully and Fischer. This cosmic background, once considered uniform, now revealed itself as a profound speedometer, painting an undeniable picture of our galaxy's restless journey and hinting at the unseen gravitational leviathan orchestrating it all. It was a problem solved, but as always, this solution led to an even deeper problem. the precise identity of this unseen hand, the evidence mounted overwhelming and undeniable. The collective flow of galaxies meticulously measured by R, Brent Tully and J, Fischer converged with the stark temperature bias in the cosmic microwave background CMB, a profound dipole confirming our motion against the universe's oldest light. Both lines of inquiry from the local galactic dance to the cosmic whisper pointed to the same cosmic truth. Our Milky Way, along with thousands of its galactic neighbours, was being pulled by an unseen force, a gravitational leviathan lurking beyond the veil of our own galaxy, past the obscuring zone of avoidance. It was given a name that echoed its immense and mysterious power. The Great Attractor. Imagine a cosmic whirlpool vast beyond comprehension, drawing in everything within its formidable gravitational embrace. This wasn't a localized anomaly. This was a force encompassing thousands of galaxies, each containing hundreds of billions of stars and countless worlds like moths to a flame, their entire galactic homes caught in an inescapable slow-motion cascade. The Great Attractor represented a monumental gravitational well, a hyperdensity of matter, both visible and dark, whose combined mass exerted a dominant pull on our entire corner of the universe. Its existence inferred purely by its gravitational signature, the observed peculiar velocities of galaxies, and the CMB dipole presented a profound problem. How could such a titanic structure remain hidden? And what were its true dimensions and composition? Its very invisibility in optical light, largely due to its position behind the Milky Way's dust lane, only heightened its mystique. The revelation of the Great Attractor solidified the understanding that the universe is far from static. From the grand cosmic scale of superclusters being drawn across millions of light years to the intimate dance of stars within a galaxy, everything is in ceaseless motion. This dynamic reality defied the long-held notion of a universe in perfect, unchanging equilibrium. The unsettling drift of our Milky Way was not an isolated incident. It was part of a universal restlessness, a fundamental property of a cosmos governed by gravity. This concept of pervasive motion challenged centuries of human perception. For millennia, humanity had anchored its existence to the seemingly unmoving Earth, then to a central sun. But the discovery of the Great Attractor meant that even our galactic home, our vast stellar island, was not a fixed point, but a particle in a much grander unseen current. It shifted our cosmic perspective, once more reinforcing the idea of a boundless dynamic cosmos where stillness is merely an illusion. The Great Attractor became a symbol of the unknown, a powerful reminder that our journey of discovery is far from over. Its presence not only explained the observed galactic flows, but also opened up a new frontier in cosmology, prompting deeper questions about the nature of dark matter, the distribution of matter in the universe, and the true extent of these gravitational behemoths. The universe, we were learning, is inherently dynamic, a roiling, churning expanse where everything is in ceaseless motion. From the gentle rotation of Earth beneath our feet to the majestic drift of entire galaxies, stillness is merely an illusion, a temporary cessation in a universe born in motion and forever bound to its restless dance. This magnificent cosmic ballet was now revealed in a new profound light. The discovery of the Great Attractor, an unseen hand pulling our galaxy through the cosmic currents, and the evidence from the cosmic background's whisper that confirmed this motion, presented a profound challenge to millennia of human understanding. For centuries across diverse civilizations, from the philosophers of ancient Greece to the brilliant scholars of the Islamic Golden Age, a deeply ingrained belief held sway. The Earth was the unmoving center of the universe. This geocentric model, championed by figures like Aristotle, and later formalized by Claudius Ptolemy in his Almagest in the 2nd century CE, resonated deeply with human perception and intuition. The ground beneath our feet felt utterly still, and the heavens, a pristine sphere adorned with stars and planets, appeared to revolve gracefully around it. Thinkers like Ptolemy in the Roman Empire, or later Islamic astronomers such as al-Biruni and Ibn al-Haytham, developed intricate models, mathematical masterpieces of their time, to explain the seemingly complex paths of the celestial bodies. Their diagrams were a symphony of nested circular orbits, epicycles and equants, each layer meticulously crafted to account for observed phenomena like the retrograde motion of Mars, where a planet would appear to temporarily reverse its direction across the sky. While these models, such as the Ptolemaic system, were remarkably predictive for their era, allowing for accurate calendar calculations and astrological forecasts, they were inherently cumbersome. They relied on an ever-increasing complexity of circles upon circles to account for observed irregularities and maintain the Earth's central static position. Yet the core assumption remained unchallenged. Earth was static, the firmament in constant motion around it. Why would one doubt the evidence of their own senses? This intellectual scaffolding, built upon careful observation and ingenious mathematics, presented a universe designed with humanity at its core, a stable, unmoving anchor in the celestial dance. The philosophical implications were significant. If Earth was the centre, it suggested a unique, perhaps even divine status for humanity within the cosmos. This worldview, reinforced by religious doctrine in many cultures, provided a comforting sense of cosmic order and purpose. The adherence to a geocentric model was not simply due to a lack of observational tools, it was a testament to the powerful hold of immediate human experience and established philosophical frameworks. To suggest that the Earth itself moved at incredible speeds, hurtling through space, would have raised immediate common sense objections. Why do we not feel this motion? Why are we not thrown off? These questions, seemingly simple, held immense power in solidifying the belief in an unmoving Earth. It was a comfortable worldview, one that satisfied both spiritual and scientific inclinations of the time, and it would take a bold, almost reckless act of intellectual courage to dismantle it. The stage was set for a profound paradigm shift, a moment when humanity would finally reckon with the unsettling truth of its own motion, a truth that would resonate for centuries to come, challenging the ancient firmament. The centuries-old edifice of the geocentric universe, with its ancient firmament of an unmoving Earth, began to crack in the early 16th century, not with a violent tremor, but with the quiet, meticulous work of a Polish polymath. Nicholas Copernicus, a mathematician, astronomer, and canon, challenged the very foundation of cosmic understanding. His magnum opus De Revolutionibus Orbium Coelestium, on the revolutions of the heavenly spheres, published in 1543, the year of his death, proposed a radical new cosmology. It was a heliocentric system, placing the Sun, not the Earth, at the centre of the universe, and setting our planet, along with all others, into a majestic orbital dance around it. This was no mere mathematical adjustment, it was a profound philosophical and observational leap. Copernicus argued for a simpler, more elegant model, one that explained the complex, seemingly erratic retrograde motion of planets as a natural consequence of Earth's own faster orbit around the Sun, rather than requiring an ever-growing tangle of epicycles and equants. By setting the Sun at rest and Earth in motion, he inverted the perceived reality of ages, daring to suggest that our familiar world was not the fixed point of creation, but a fellow wanderer in a larger cosmic scheme. This daring proposal, though revolutionary, was initially met with a mix of cautious intrigue and outright skepticism. While it elegantly simplified certain aspects of celestial mechanics, it immediately raised profound and intuitive questions for his contemporaries. If the Earth truly spun on its axis at incredible speeds, why did we not feel it? Why were we not flung off into the vast emptiness of space? If it hurtled through its orbit around the Sun, why was there no perpetual hurricane-force wind constantly rushing past us? And why indeed were birds not left behind, unable to keep pace with the rapidly moving ground? These were not trivial objections, they were visceral challenges to a concept that defied everyday perception, echoing the very human experience that had anchored the geocentric model for so long. The absence of apparent physical effects of the sensation of hurtling through space seemed to provide irrefutable proof that our world remained fixed. The early Copernicans grappled with these challenges, offering explanations that, while logical, often felt abstract compared to the tangible reality of a calm, stationary world. It highlighted the deep chasm between immediate human perception and the profound, often counterintuitive truths of the cosmos. The challenge was not just to prove Earth's motion mathematically, but to explain why that motion remained hidden unperceived by the very beings experiencing it. Copernicus's revolution was less an immediate overthrow and more a planting of a seed, a fundamental shift in perspective that would slowly but surely blossom into the modern understanding of a dynamic, moving universe. preparing the way for future discoveries about even grander cosmic motions like the unsettling drift of our Milky Way. The universe, it seemed, had a remarkable way of keeping its grandest secrets close, waiting for the right mind and the right moment to unveil them. Copernicus's heliocentric model, a daring proposal that shifted the sun to the center of our local cosmos, immediately raised profound questions that resonated deeply with common sense and human experience, challenges that the ancient firmament of an unmoving Earth had never had to face. If the Earth truly spun on its axis at incredible speeds, why did we not feel it? Why were we not flung off into the vast emptiness of space? This was the intuitive concern, a visceral problem that seemed to contradict the very idea of a moving Earth. Imagine standing on a rapidly spinning carousel. You feel the outward pull, the sensation of being about to be thrown off. Why then did the inhabitants of Earth not feel a similar force, a constant tug against their very being? If Earth hurtled through its orbit around the Sun at tens of kilometers per second, why was there no perpetual hurricane-force wind constantly rushing past us? And why indeed were birds not left behind, unable to keep pace with a rapidly moving ground? These were not trivial objections from a scientific perspective of the 16th century. They were intuitive, seemingly unassailable challenges to a concept that defied everyday perception and the direct experience of a calm, stationary world. For centuries, these very questions had been powerful arguments against any form of Earth motion. The unshakable experience of standing on seemingly solid ground, utterly still, was a powerful counterargument to any theoretical astronomical acrobatics. The absence of apparent physical effects of the sensation of hurtling through space seemed to provide irrefutable proof that our world remained fixed. The early Copernicans, such as Georg Joachim Rheticus, Copernicus's only student, published on his work, and later Galileo Galilei, grappled with these challenges. They offered explanations rooted in the concept of relative motion, arguing that if everything around us moved with us, we would not perceive the motion. But these arguments, while logical to a trained mind, often felt abstract and insufficient compared to the tangible reality of a calm, stationary world for the general populace. It highlighted the deep chasm between immediate human perception and the profound, often counterintuitive truths of the cosmos. The challenge was not just to prove Earth's motion mathematically, but to explain why that motion remained hidden unperceived by the very beings experiencing it. This problem, the weight of movement and its unseen forces, would vex natural philosophers for over a century, demonstrating the deep resistance to new scientific paradigms when they clashed so fundamentally with intuitive experience. The universe, it seemed, had a remarkable way of keeping its grandest secrets close, waiting for the right intellectual leap and the development of new physical laws to fully unveil the truth of its ceaseless motion from our planetary home to the unsettling drift of our entire galaxy. It was a testament to the fact that sometimes the most profound truths are those that are least immediately apparent to our senses. The powerful intuition that resisted Copernicus's vision, the nagging questions of why we don't feel Earth's motion, the weight of movement that seemed to contradict the daring proposal of a heliocentric system, finally found its satisfying resolution with the towering intellect of Isaac Newton. In his monumental work Philosophia Naturalis Principia Mathematica, commonly known as Principia Mathematica, published in 1687, Newton laid down the universal laws of motion and gravitation laws that would transform our understanding of the cosmos and crucially explain why the Earth's movement remains imperceptible to us. Newton's genius revealed that we do not feel the Earth's motion because we and everything around us, the air, the buildings, the very ground, are moving with it as a single cohesive system. His first law of motion, the law of inertia, states that an object in motion will stay in motion with the same speed and in the same direction unless acted upon by an unbalanced force. We are constantly in motion, with the Earth experiencing no relative acceleration within our immediate frame of reference. Imagine being inside a smoothly moving train. Without looking outside, you feel no motion relative to the train itself. You can walk, jump, and pour a drink as if you were standing still because you share the train's velocity. Similarly, we are passengers on a cosmic vessel bound by gravity, travelling smoothly through the near-perfect vacuum of space. There is no external air resistance, no drag to create the sensation of a rushing wind that would constantly push against us. Gravity, the unseen force that binds us to the Earth and the Earth to the Sun, ensures that we share its colossal momentum. Newton's universal law of gravitation provided the mathematical framework to understand this embrace. Every particle of matter attracts every other particle with a force directly proportional to the product of their masses and inversely proportional to the square of the distance between their centres. This elegant universal law explained how celestial bodies maintain their orbits from the moon around the Earth to the planets around the Sun, and indeed how everything on Earth stays firmly attached. There is no fixed anchor against which to feel our hurtling journey. The absence of apparent forces that would pull us off a spinning Earth or create a gale from its orbital speed was precisely what one would expect from a massive body moving freely and uniformly through space under the influence of gravity. Newton's laws elegantly explained that the seemingly contradictory absence of sensation was in fact precisely what one would expect. He transformed a perplexing paradox, the silent journey, into a profound confirmation of a dynamic, interconnected universe. The Earth was indeed in motion, engaged in its celestial dance, and we, its inhabitants, were its silent, unwitting companions on a cosmic voyage. Newton's unveiling of the embrace of gravity not only validated Copernicus, but also paved the way for deeper explorations of motion on scales far beyond our solar system, leading eventually to the understanding of the unsettling drift of our entire galaxy. This marked a monumental step in humanity's quest to truly comprehend its place in a restless cosmos. If Isaac Newton, with his unveiling of gravity's embrace, explained why we don't feel Earth's motion, Albert Einstein, with his revolutionary theories of relativity, took the concept of motion itself to an even more profound philosophical and physical level. Einstein's theories, primarily special relativity 1905 and general relativity 1915, fundamentally rejected the notion of an absolute fixed reference frame in the universe, a cosmic backdrop against which all other motion could be precisely measured. Instead, all inertial motion, that is, motion at a constant velocity without acceleration, is inherently relative. Imagine two spaceships, Ship A and Ship B each, moving at a constant speed in a vast empty expanse. From the perspective of an observer on Ship A, Ship B is moving, but from the perspective of an observer on Ship B, Ship A is moving. Neither can claim to be absolutely at rest. Both are equally valid inertial observers, and the laws of physics are the same for both. Their motion is only meaningful in relation to each other, a constant shifting dance of relative velocities. This elegant principle, while disorienting at first for a universe long conceived with a fixed centre, revealed a deeper truth about the universe. Motion is not an absolute state, but a relationship, a shifting sands of reference. However, this doesn't mean all motion is purely subjective or undetectable. Acceleration, a change in velocity, either speed or direction, is absolute. This is where the universe's dynamism becomes palpable. Earth's spin, for instance, generates very real measurable effects due to its acceleration. The Coriolis force, a direct consequence of our planet's rotation, is a fascinating example. This apparent force deflects moving objects, winds, ocean currents, even projectiles, to the right in the northern hemisphere and to the left in the southern hemisphere. This deflection is precisely why large weather systems like hurricanes and cyclones spin in opposite directions in different hemispheres. Even without external stars for reference, the very dynamics of our atmosphere betray our planet's constant silent pirouette. We feel the effects of our rotation, not our constant velocity. Einstein's insights didn't deny motion. They redefined it, transforming the rigid framework of absolute space and time into a fluid, interconnected dance, where every movement is part of a grand relative symphony. His work laid the theoretical groundwork for understanding peculiar velocities on a cosmic scale, demonstrating that while the total velocity of our galaxy against the cosmic microwave background is a fixed value, how we perceive it depends on our chosen reference frame. This deep understanding of relative motion was crucial for future astronomers like Tully and Fischer, who, when charting the unsettling drift of the Milky Way, had to account for all these layers of motion before they could isolate the true collective flow towards the Great Attractor. The universe, it seemed, was even more dynamic and interconnected than we had dared to imagine, with its grandest secrets often hidden in plain sight, waiting for a revolutionary mind to reveal their true relativistic nature. The vast undulating sea of space revealed by the cosmic background's whisper was not as serene as once imagined. For centuries, humanity dreamt of an unmoving Earth, a fixed point in the celestial dance, a dream shattered first by Copernicus's daring proposal, then by Newton's gravitational embrace, and finally by Einstein's declaration that all motion was relative. We learned our homeworld hurtled through the void, that our sun was a star among billions, ceaselessly orbiting the galactic core. But the universe we now understood held yet another layer of profound, unsettling motion. Imagine, if you will, a mariner cast adrift on a vast, limitless ocean. From their tiny vessel they observe all the great rafts of seaweed, all the scattered flotsam around them, appearing to recede, moving away, as if the very surface of the water beneath them were stretching. This, in essence, is the grand majestic Hubble flow, the expansion of the cosmos pulling galaxies apart, stretching the fabric of space-time itself. It is the baseline, the expected, the universal current upon which all things are born. Yet our mariner, even as distant flotsam recedes, might notice something more immediate, more localized. Their own boat might be subtly nudged by an unseen undertow, pulled slightly off course by a deep, powerful current known only to the immediate vicinity. This unpredicted drift, this subtle yet significant deviation from the great outward flow, is what we, the intrepid cartographers of the cosmos, have come to call peculiar velocity. It is the motion that deviates from the universal expansion. Every galaxy, every magnificent island of stars participates in the Hubble flow. It is carried along by the stretching space, but each galaxy also possesses its own unique local movement. Influenced by the gravitational whispers of its immediate neighbours, the powerful tugs of nearby clusters, and the colossal unseen hand of the Great Attractor. This is the peculiar velocity, the individual, often surprising journey of a cosmic island through the expanding ocean. For decades, this subtle secondary motion remained largely invisible, masked by the overwhelming grandeur of the universe's expansion. How could one discern a ship's personal drift when the entire ocean was expanding? The challenge was immense. To separate the universal recession from the local shuffle, this is where the pioneering spirit of astronomers like Tully and Fischer became indispensable. Their groundbreaking work, which transformed spiral galaxies into standard candles by linking their intrinsic luminosity to their rotation speed, provided a cosmic compass, a way to measure true distance independent of redshift. By knowing a galaxy's intrinsic brightness, and thus its true distance, we could predict how fast it should be receding from us due to the Hubble flow. When that predicted recession speed didn't perfectly match the observed redshift, the difference was the galaxy's peculiar velocity. It was a detective story where the discrepancy between expectation and observation revealed the hidden truth. The most profound and personal confirmation of peculiar velocity came from the cosmic background's whisper, that faint ancient light from the universe's infancy. When Chapter 4 revealed the dipole in the cosmic microwave background, a subtle but unmistakable hotter patch on one side of the sky, and a colder patch on the other, it was a seismic shock. This wasn't a feature of the early universe itself, it was a Doppler shift. It was the undeniable imprint of our own motion. Our galaxy, the Milky Way, was hurtling through space relative to the universe's most ancient light, moving at hundreds of kilometers per second towards the constellation Leo. This dipole was the direct evidence, the unmistakable fingerprint of our peculiar velocity. And what was driving this immense, ceaseless journey? Chapter 5 introduced the Great Attractor. The unseen hand, a colossal diffuse concentration of mass gravitationally pulling our local group and countless other galaxies towards it. The peculiar velocities we measured for our galaxy and others in our vicinity pointed like invisible arrows towards this unseen behemoth, confirming its gravitational dominion. The concept of peculiar velocity redefines our place in the universe once more. It tells us that while we are part of the grand cosmic expansion, we are not passively carried along. We are also active participants in a more intricate local dance of gravity shaped by the ebb and flow of cosmic structures. It is a constant reminder that the universe, even in its most predictable moments, holds unexpected currents and unseen forces guiding our journey through the boundless dark. Each peculiar velocity becomes a data point, an arrow on a cosmic map, sketching out the invisible landscape of mass that truly governs the universe's grand ballet. It is the subtle signature of the universe's true three-dimensional tapestry. When we speak of cosmic motion, of the unsettling drift of our galaxy, or the shifting sands of reference in Einstein's relative universe, it's easy to dismiss it as an abstract concept relevant only to distant galaxies. But the truth is, we're all participants in this grand cosmic ballet, experiencing speeds that would boggle the imagination if we could truly feel them. Our journey through the cosmos is a composite of multiple layers of motion, each adding to our incredible unseen velocity. To truly appreciate the scale of our peculiar velocities and the cosmic compass against which they are measured, we must first understand our own unseen journey, quantifying the drift of our very selves. Consider just our local journey. The Earth beneath our feet spins on its axis, completing one rotation approximately every 24 hours. At the equator, this rotation carries us at speeds up to 1670 km per hour, about 1038 miles per hour. While this speed decreases as one moves towards the poles, it is still a significant velocity. Over the course of an average human lifespan of 80 years, this rotation alone carries us through a staggering distance of approximately 17 billion kilometers. That's equivalent to traversing the entire diameter of the Sun, almost 850 times every year, all without the slightest sensation of movement. But that's just the spin. Our planet is also locked in a colossal orbit around the Sun, hurtling through space at an astonishing speed of approximately 30 kilometers per second, about 67,000 miles per hour. In a single year, that's nearly 940 million kilometers. Over an 80-year lifetime, our orbital journey totals approximately 75 billion kilometers, a distance almost beyond comprehension. It is a silent, unceasing rush through the vacuum, a majestic dance that defines our seasons and our very notion of a year. The precision of this orbital speed is critical. Too slow and Earth would spiral into the Sun. Too fast and it would be flung into the cold reaches of outer space. Beyond our planet's immediate vicinity, our entire solar system is on the move. The Sun itself is part of a vast collective motion within the Milky Way. Our local star, with Earth and all its planetary companions in tow, revolves around the colossal heart of our own galaxy. The Sun's velocity in this grand circuit is a staggering 230 kilometers per second, about 514,000 miles per hour. At this speed, it takes our solar system approximately 230 million years to complete one revolution around the galactic center, a period known as a cosmic year. In an 80-year human lifespan, we complete only about 1/3 millionth of a cosmic year, traveling roughly 580 billion kilometers as part of this galactic carousel. These are not just numbers on a page. They are the rhythms of our existence, the unseen forces that define our physical presence in the cosmos. We are each of us intrepid cosmic travelers charting distances that dwarf our terrestrial experiences, propelled by the same fundamental forces that shape the movements of galaxies. And yet we feel nothing a testament to the elegant laws of physics elucidated by Newton and Einstein that govern our magnificent restless journey. These incredible speeds are just the beginning of our cosmic address, a prelude to the even grander motions that shape our galaxy's journey towards the Great Attractor. Beyond our planet's local dance and the intricate quantification of our own unseen journey through space, our entire solar system is caught in a much larger, more majestic motion, an orbit around the colossal heart of our own Milky Way galaxy. The Sun, with Earth and all its planetary companions in tow, completes one revolution around the galactic center, approximately every 230 million years, a period known as a cosmic year. Our speed in this grand circuit, this Milky Way's whirl, is a staggering 230 kilometers per second, nearly 500,000 miles per hour. This speed is vital, for it is the precise velocity required to prevent our solar system from either spiraling inward into the supermassive black hole at the galactic core, or being flung out into the cold, dark emptiness of intergalactic space. Yet this majestic speed and the remarkable stability of our galaxy presents a profound cosmic mystery. When astronomers calculate the gravitational pull exerted by all the visible matter in the Milky Way, the stars, gas and dust that glow so brightly, which we can directly observe and measure, they find it utterly insufficient to keep our solar system, and indeed the entire galaxy, from flying apart. According to the laws of Newtonian gravity, if only the visible matter were present, stars and gas clouds at the outer edges of the galaxy should be orbiting much slower than observed, or they should simply escape the galaxy's gravitational grip. At our observed speed, the Milky Way should have long ago unravelled its constituent parts, scattered into the void akin to a rapidly spinning carousel from which all the riders are flung off. This glaring discrepancy, this gravitational deficit, was one of the earliest and most compelling pieces of evidence for the existence of something unseen, something profound, dark matter. The problem, which emerged prominently from the work of pioneering astronomers like Vera Rubin and Kent Ford in the 1970s, lay in the galaxy's rotation curve. They observed that stars and gas clouds far from the galactic centre were orbiting just as fast, if not faster, than those closer in. This flat rotation curve was inexplicable if visible matter alone dictated gravity. It suggested a vast invisible halo of mass enveloping the entire galaxy, extending far beyond the luminous disk. This mysterious invisible substance, which we now call dark matter, is theorized to compose over 80% of the universe's matter content, yet it does not interact with light or other electromagnetic radiation, making it utterly invisible to our telescopes. It is dark not because it blocks light, but because it emits no light and interacts with normal matter only through gravity. It is this pervasive unseen halo of dark matter that provides the additional gravitational glue necessary to hold galaxies like ours together, allowing us to complete our colossal, elegant orbital dance. The very stability of our galactic home, its whirl, and our continued presence within its spiralling arms is a profound testament to the hidden hand of dark matter, solving the problem of galactic stability only to reveal a deeper, more fundamental mystery of the cosmos. This unseen hand of dark matter, distinct from the Great Attractor's influence, is a foundational component of our cosmic address. The Milky Way's journey through the cosmos is not just a smooth, flat orbit defined by the Milky Way's whirl and the pervasive influence of dark matter. It's a dynamic, three-dimensional dance. As our solar system revolves around the galactic centre, completing its colossal 230 million year circuit, it also engages in a gentle vertical oscillation, a galactic bob moving up and down through the galactic plane. Imagine a tiny cork on a vast churning sea. This gentle undulation, driven by the gravitational pull of the galactic disk's visible and dark matter, means that our solar system periodically traverses denser and sparser regions of our galactic home. This cycle, taking roughly 60 million years to complete one full bob up and down, plays a subtle but significant role in shaping our cosmic environment. One of the most remarkable results of this vertical bob is our current location within what is known as the local bubble. Imagine a vast cavernous void hundreds of light years across, carved out of the interstellar medium. This is the local bubble, a region of remarkably low density gas and dust, with a temperature far hotter than typical interstellar space, around 1,000,000 degrees Celsius. This scorching yet incredibly tenuous cavity was created eons ago by a series of powerful supernova explosions. These cataclysmic stellar deaths, the final explosive gasps of massive stars from what were once nearby OB associations, clusters of hot, luminous, short-lived stars, created colossal shockwaves that swept away the surrounding interstellar material, leaving behind a relatively empty hot cavity. Our solar system entered this cosmic oasis approximately 5 to 10 million years ago, providing us with a clearer view of the distant universe, less obscured by the intervening gas and dust that characterizes the denser regions of the galactic plane, and indeed the problematic zone of avoidance. Our passage through this transparent bubble has allowed us an unobstructed view of the cosmos, facilitating the very observations that led to the discovery of the unsettling drift of our galaxy and the Great Attractor. This fortunate position has been a boon for observational astronomy, offering a clear window to the universe beyond our immediate galactic confines. Our current presence within this vast supernova-carved cavity is a stark reminder that even within the grand scale of the Milky Way, our immediate cosmic environment is a restless, evolving place shaped by the violent drama of stellar life and death. The galactic bob ensures that our journey is not just a flat two-dimensional orbit, but a rich three-dimensional traverse through a constantly changing interstellar landscape. It highlights the dynamic interplay of stellar evolution and galactic structure, illustrating how even seemingly local events, like the explosive demise of massive stars, can sculpt the cosmic environment on scales far beyond their immediate impact. This constant motion, this perpetual reshaping of our cosmic environment, is yet another layer in the complex story of our galaxy's boundless journey through the universe. The night sky, a canvas of ancient unwavering stars, has always been the ultimate symbol of constancy, a firmament upon which humanity has charted its destiny. JH6. For millennia, from the earliest watchers to the bold visionaries like Copernicus, Keach 7, who dared to re-evaluate our place, the stars seemed fixed eternal. But like all grand illusions, this too is destined to shatter. Imagine a night incomprehendibly far in our future, perhaps 4-5 billion years from now. A child, let's call her Elara, gazes upwards from a planet that might not even be Earth, but a world spun from its legacy. The familiar ribbon of the Milky Way, our galactic home, is no longer the sole monarch of the heavens. Instead, a ghostly spiral, larger, brighter, dominates the celestial sphere. It hangs like a cosmic twin, its arms reaching its core, a blazing heart. This isn't just a distant galaxy. This is the Andromeda galaxy, our largest neighbour, and it is hurtling towards us. For centuries, astronomers knew Andromeda as M31, a magnificent island universe, a smudge visible even to the naked eye under dark skies. But it was Edwin Hubble, with his groundbreaking observations, who truly established its extragalactic nature, proving it was a galaxy in its own right, not merely a nebula within our own. Yet even with that revelation, its true relationship to us remained a mystery. It wasn't until the meticulous work on peculiar velocities Chi 11 began to paint a fuller picture of cosmic motion that the unsettling truth emerged. We know thanks to the methods pioneered by Vera Rubin, who quantified the invisible forces within galaxies, and the work of scientists like Tully and Fischer 3, who measured galactic distances through rotational speeds, that our universe is a place of constant swirling movement. Every galaxy, every star indeed, every particle is locked in a colossal, intricate ballet orchestrated by the invisible hand of gravity. 9. Our own sun. Our solar system is not stationary but part of a grand unseen journey, Sestra, a journey quantified by the dipole revealed in the cosmic background's whisper, just 4. The local bubble Sh14 that cradles us is itself adrift on this cosmic tide. While most galaxies are receding from us, pulled apart by the expanding fabric of space-time itself, a select few are drawn together by the sheer gravitational might of nearby colossal structures. Andromeda is one such exception. Its light, unlike the red-shifted glow of receding galaxies, exhibits a blue shift, a subtle compression of its light waves that tells us unequivocally that it is approaching. Not drifting apart, but closing in at an astonishing speed of roughly 110 km per second, or nearly 400,000 km per hour. This isn't a mere flyby, this is an inevitable embrace, a cosmic collision of monumental scale. But for all the drama the word collision evokes, it will be unlike anything humanity has ever witnessed. Galaxies are vast, mostly empty spaces. Stars, for all their countless numbers, are infinitesimally small points separated by colossal gulfs. When the Milky Way and Andromeda merge, direct star-on-star impacts will be incredibly rare, almost non-existent. The elegant spiral arms, the familiar forms we see today, will be ripped apart only to reassemble into something new. Instead, imagine two grand swirling storm clouds passing through each other. Their vast reservoirs of gas and dust will collide with spectacular force, igniting immense bursts of star formation. The gravitational fields of both galaxies will warp and intertwine, flinging stars into new chaotic orbits. Our solar system might be tossed to the outer reaches of the newly formed galactic behemoth, or perhaps drawn to its active core. The Sun itself will remain largely unscathed, continuing its quiet, consistent fusion, its fate tied more to its own stellar evolution. Over billions of years, the two distinct spirals will lose their individual identities, their majestic arms dissolving into a chaotic jumble of stars, gas, and dark matter. Cheech 13. This simple gravitational attraction, playing out over incomprehensible timescales, will culminate in a new complex reality. Eventually, this cosmic maelstrom will settle, coalescing into a single colossal elliptical galaxy, a new entity tentatively named Milkdromeda or Milkdromeda, a grand new structure born from the fiery demise of two ancient ones. This future distant beyond human comprehension is a direct consequence of the universal laws Newton G9 unveiled and Einstein G10 refined. It is the inexorable pull of mass, the relentless dance of cosmic bodies playing out on the scales that dwarf our very existence. The universe, in its raw, unfiltered glory, does not care for our definitions of stillness or permanence. It is a dynamic, ever-changing tapestry, and our galaxy, the Milky Way, is but a single thread being rewoven into a new, unimaginably grand design. This approaching colossus is not an end, but a new beginning, a testament to the ceaseless, beautiful, and sometimes terrifying evolution of the cosmos. The collision of the Milky Way and Andromeda, an approaching colossus that will reshape our galactic future, is not an instantaneous cataclysm, but a slow-motion cosmic dance unfolding over billions of years. Imagine the grandeur of the night sky, its familiar constellations, and the majestic band of our Milky Way. Now fast forward 2 billion years into the future. The skies above Earth, or whatever planetary system might then inhabit our solar neighbourhood, would be utterly transformed. Andromeda, currently a faint smudge visible only in pristine dark skies, would dominate the celestial sphere. Its vast spiral arms, distorted by the mutual gravitational tug-of-war, would stretch across a significant portion of the night, a breathtaking and unsettling spectacle. As the galaxies draw nearer, the gravitational interactions would begin to exert powerful tidal forces on both systems. These forces would stretch and pull the galaxies into bizarre elongated forms, ripping apart their delicate spiral structures. Long, luminous tidal tails of stars and gas would be torn from the merging galaxies, stretching for hundreds of thousands of light years, creating breathtaking cosmic vistas that would paint the heavens with an ethereal glow. These celestial streamers, like the trailing garments of cosmic dancers, are a signature of galactic interactions observed in the universe today, offering a glimpse into our own future. By 4 billion years from now, the skies would not just be dominated by Andromeda. They would blaze with an intensity unimaginable today. The immense gravitational forces at play, the compression of vast gas and dust clouds, and the shock waves generated by the colliding interstellar mediums would trigger an explosion of star formation, 1,000-fold greater than current rates in either galaxy. New stars, brilliant and blue, would ignite across the colliding galaxies with furious intensity, painting the cosmic canvas with an incandescent fury. This would be a period of unprecedented celestial fireworks, a cosmic reawakening driven by the immense energy released in the galactic merger. Entire nebulae, once quiet nurseries, would burst into life, illuminating the merging arms with the raw power of stellar birth. While direct stellar collisions between individual stars would remain incredibly rare, due to the vast distances between them, the overall environment would be one of incredible dynamism. Planetary systems might find their orbits perturbed, perhaps gently shifting, or in some extreme cases being flung into the cold intergalactic void. The cosmic dance foretold is a stunning vision of our galactic future, one where the familiar comfort of our current night sky gives way to a dynamic, fiery panorama, a testament to the relentless transformative power of gravity on the grandest scales. The universe is a master artist, and its next masterpiece is already being drafted, promising a sky transformed into a spectacle of unparalleled grandeur and a fundamental restructuring of our galactic home. This chaotic beauty is a necessary prelude to the next stage of our cosmic evolution, the cosmic ballet between the Milky Way and Andromeda. After billions of years of gravitational embrace and fiery star formation that will transform the sky, will eventually reach its grand finale. Approximately 5 billion years from now, the two colossal spirals will have fully merged their distinct identities, dissolving into a single majestic new galaxy. This celestial offspring has already earned a playful yet fitting name among astronomers, Milkdromeda. But Milkdromeda will be no ordinary spiral. It will be an elliptical galaxy, a vastly different form from its progenitors, representing an elliptical aftermath. Imagine two dancers twirling furiously, their distinct forms blurring into one. As the merger completes, the vast reserves of gas and dust previously compressed and ignited into a furious burst of star formation will largely be depleted. The furious starbursts will subside, leaving behind a galaxy dominated by older redder stars, much like the giant elliptical galaxies we observe across the universe today. It will be a quiescent giant, its vibrant star-forming days largely behind it, a testament to the finite nature of cosmic fuel. The process of merging effectively consumes the gas and dust that fuels starbirth. While the individual stars within Milkdromeda will rarely collide, the vast distances between them ensuring they mostly pass harmlessly by one another, their orbits will be drastically reshaped. The orderly, nearly circular orbits characteristic of spiral arms will be replaced by a more chaotic, less organised structure, with stars moving on highly elongated eccentric paths. This gravitational scrambling will transform the flat disc-like structure of the spirals into a more three-dimensional, roughly spherical or ellipsoid shape typical of elliptical galaxies. Some stars and even entire star clusters will be flung to new, often more distant trajectories, perhaps even ejected entirely from the nascent merged galaxy into the cold intergalactic void, becoming lonely wanderers in the dark. Furthermore, the supermassive black holes at the centres of both the Milky Way and Andromeda Sagittarius A, and Andromeda's own colossal black hole, will eventually spiral inward and merge. This will result in an even more massive central black hole, a gravitational leviathan at the heart of Milkdromeda. The merger itself is a chaotic long process, with simulations showing variations in the precise timing and final morphology. Some models suggest the full merger might be delayed slightly, perhaps to 8 billion years from now, or even averted if the tangential velocities are just right. However, the prevailing and most robust simulations confirm the general outcome of a vast elliptical galaxy. Milkdromeda will be a powerful yet ultimately serene monument to the universe's capacity for transformation, a final stable form born from the chaotic union of two galactic titans. Its formation will be a crowning event in the history of our cosmic neighbourhood, a dramatic culmination of the unsettling drift that began with the pull of the Great Attractor and the larger forces shaping the cosmic dance foretold. It represents a deep problem solved only to reveal the deeper problem of the ultimate fate of such a colossal structure in an expanding universe. For much of human history, the Andromeda Nebula was just that, a fuzzy patch of light, a celestial smudge in our night sky visible even to the naked eye as a faint elongated smear. Its true nature was shrouded in mystery. Was it a cloud of gas and dust within our own Milky Way, a nascent star system perhaps, or something far grander, an island universe akin to our own? The scientific debate raged for decades, reaching a fever pitch in the early 20th century, a reflection of the limits of our observational capabilities and the prevailing theories of our place in the universe. It took the keen eye and relentless dedication of one of the greatest astronomers of the 20th century to finally settle the matter and embark on Hubble's Andromeda revelation. Edwin Hubble, a meticulous and visionary observer working in the 1920s, with the aid of the powerful 100-inch Hooker telescope at Mount Wilson Observatory in California, embarked on a painstaking study of the Andromeda Nebula. This was at the time the largest telescope in the world, granting Hubble unprecedented clarity and light-gathering power. His breakthrough came with the observation of Cepheid variable stars within the Andromeda Nebula. These particular stars are cosmic lighthouses pulsating with a predictable rhythm, and crucially their period of pulsation is directly related to their intrinsic luminosity. How bright they truly are. Henrietta Swan, Leavitt's earlier work on Cepheids, had provided the critical period luminosity relation, turning them into reliable standard candles for measuring cosmic distances. By meticulously comparing the apparent brightness of the Cepheids in Andromeda to their known intrinsic brightness, Hubble could determine their true distance. His calculations were revolutionary. The Cepheids in Andromeda were found to be millions of light-years away, far, far too distant to be part of our own Milky Way. Andromeda was not a nebula within our galaxy. It was an entirely separate vast island universe, a galaxy in its own right lying approximately 5 million light-years away. This monumental discovery, published in 1929, provided the first irrefutable proof of galaxies beyond our own fundamentally reshaping our understanding of the cosmos, expanding its scale and complexity almost infinitely overnight. Hubble's revelation transformed our universe from a single stellar island into a boundless ocean of galaxies, each a distinct cosmic address, each on its own unique journey. It was a profound shift in cosmological thought, moving from a relatively contained island universe model to the vast universe of galaxies. This discovery laid the foundation for modern cosmology, enabling future astronomers like Tully-Fischer to understand the grand movements of galaxies and the unsettling drift of our Milky Way, not just as isolated phenomena, but as part of a much larger interconnected cosmic web. Hubble had in essence unmasked a giant unveiling a universe far grander than anyone had dared to imagine, and setting the stage for the next great question. How did these galaxies interact? The ancient firmament held its secrets close, its vast expanse a canvas of perceived stillness. For epochs, humanity gazed upon the luminous smudge of Andromeda, a sister galaxy knowing only its radiant presence. But as our understanding of the cosmos deepened, a profound, unsettling truth emerged. Andromeda was not merely a distant beacon, it was a cosmic titan hurtling towards us. Chapter 15 had painted the inevitability of this approaching colossus, a galactic embrace foretold. Yet an ancient fundamental question lingered, one that held the key to our cosmic fate. Was this a mere passing brush, a celestial waltz, or a true head-on collision? The initial whispers of Andromeda's intent came from its radial velocity, the measurement of its motion directly towards or away from us. Just as a siren's pitch shifts with the speed of an ambulance, so too does a galaxy's light betray its approach or retreat. The Doppler effect, that elegant cosmic compass, had long confirmed Andromeda's relentless charge. It was rushing towards the Milky Way at an astounding 110 kilometers per second. This confirmed our shared journey, our entangled destinies. But a galaxy's motion is not a simple one-dimensional dot. It sweeps through the void with components both towards us and across our line of sight. It was this elusive sideways motion, what astronomers call proper motion, or tangential velocity, that remained shrouded in mystery, challenging even the most ambitious telescopic endeavours. Imagine standing on a distant world trying to discern the precise path of a ship sailing thousands of miles away, merely by watching it through a powerful telescope. You might see it getting closer, but could you tell if it would pass to your left, to your right, or crash straight into your shore? For galaxies light years away, this challenge magnified beyond human comprehension. The subtle shift of Andromeda against the backdrop of more distant, seemingly fixed stars would be imperceptible to anything but the most steadfast and precise eyes. Ground-based telescopes, however magnificent, battled the Earth's blurring atmosphere, a turbulent sea of air that rendered such minute measurements impossible. The cosmic dance remained an enigma, its choreography unknown, its outcome a terrifyingly uncertain possibility. It was into this cosmic blind spot that the noble gaze of the Hubble Space Telescope turned its instruments freed from the Earth's atmospheric veil, offering an unprecedented clarity of vision. For 7 painstaking years, from 2002 to 2010, Hubble became an unblinking eye, its gaze fixed on specific regions within Andromeda, meticulously tracking the subtle, almost imperceptible shifts of hundreds of its individual stars. This wasn't a casual glance, it was a dedicated long-term observational campaign, a triumph of scientific patience and technological prowess, a testament to humanity's unyielding quest to decode the universe's grand designs. Led by dedicated researchers like Dr. Roland van der Meyl and his brilliant team at the Space Telescope Science Institute Hubble performed repeated high-resolution observations. Each image, separated by months or years, became a precise marker in the celestial timeline. It was a grueling exercise in extreme precision, measuring angles so tiny they were equivalent to discerning the width of a human hair from 10 miles away. A feat of observational astronomy that pushed the boundaries of what was thought possible. The accumulated data was then painstakingly analysed, sifting through the noise to find the signal tracking the ghostly trails of stars within Andromeda, as they seemingly crept across the sky, their tiny movements speaking volumes. The revelation, when it finally emerged from the reams of data, was as profound as it was stark. The tangential velocity Andromeda's sideways motion was vanishingly small. It was a mere whisper compared to its roaring radial velocity. The cosmic ballet was not a graceful sidestep nor a near miss. It was a direct, unwavering trajectory, a gravitational death grip. Andromeda was not going to brush past us. It was on a collision course, its colossal mass drawn by the inescapable embrace of gravity, its path confirmed with a certainty that transcended mere prediction. The scientific twist lay not in a surprise maneuver, but in the absence of one revealing the most straightforward yet utterly dramatic outcome. This meticulous measurement by Hubble didn't just confirm an impending collision, it transformed it from a theoretical possibility into a scientific certainty, a precise forecast of our galactic future. It provided the ultimate empirical proof, a data-driven confirmation of what gravitational models had long suggested. It was a dramatic revelation, a scientific twist in the cosmic narrative underscoring the simplicity of this complexity paradox. A seemingly simple question about two galaxies meeting required decades of technological advancement, years of dedicated observation, and the persistent ingenuity of humanity's most sophisticated eye on the universe. The profound complexity hidden within that simple question now stood revealed, charting the inevitable birth of Milkdromeda, an elliptical aftermath, a transformation foretold since Chapter 17. The universe had whispered its secrets, and Hubble, our cosmic compass, had finally made them plain, charting a future where the sky would be transformed as explored in Chapter 16, leading to a new cosmic identity. The term galactic collision conjures images of cataclysmic destruction of stars smashing into each other, planetary systems obliterated. But the reality of a galactic merger, like the approaching colossus of Andromeda towards our Milky Way, is far more nuanced. It is a slow-motion cosmic ballet rather than a head-on crash, a process leading to the birth of Milkdromeda, an elliptical aftermath. Imagine two immense diffuse clouds of dust, each containing tiny, widely spaced grains. When these clouds merge, the grains rarely strike one another. So it is with galaxies. The vast distances between stars ensure that direct stellar collisions are incredibly rare even during a merger. If the Sun were a grain of sand, the nearest star, Proxima Centauri, would be another grain of sand over 100 kilometers away. The chance of two grains of sand hitting each other during a collision of two vast deserts is negligible. What does happen, however, is a profound gravitational reshaping. The immense gravitational forces between the two approaching galaxies exert powerful tidal stresses, stretching and pulling the galaxies into bizarre elongated forms. Long luminous tidal tails of stars and gas are ripped from the merging galaxies, stretching for hundreds of thousands of light years, creating breathtaking cosmic vistas. These celestial streamers, often seen in interacting galaxies, are compelling evidence of this cosmic dance. Bridges of stars and gas can form between the interacting systems, funneling material into their cores. While individual stars are safe from direct impact, their orbits are drastically disrupted. Stars are flung to new, often more distant trajectories, some even ejected entirely from the nascent merged galaxy into the cold, intergalactic void, becoming lonely wanderers in the dark. Crucially, the compression and shock waves generated by the colliding gas clouds within the galaxies trigger intense bursts of star formation, igniting new suns at rates far exceeding those of isolated galaxies. This furious starburst activity, which causes the sky to be transformed during the peak of the merger, rapidly depletes the galaxy's gas reserves, leaving the resulting elliptical galaxy red and starved of new stellar births in the long term. Astronomers study examples of galactic mergers across the universe to understand the processes that will unfold with the Milky Way and Andromeda. Observations of merging galaxies like the Mice galaxies, NGC 4676 with their distinctive long tidal tails, and ARP 220, an intense starburst galaxy, hidden by colossal amounts of dust, provide stunning snapshots of this dynamic process, offering a glimpse into our own galactic future. Computer simulations, using our understanding of gravity and cosmic gas dynamics, meticulously model these complex interactions. Though, variations in initial conditions can lead to slightly different outcomes, with some simulations delaying the final merger, or even presenting scenarios where a full head-on collision is averted in favour of a grazing pass. However, the overarching conclusion remains: Our galaxy is destined for a profound transformation, a truly galactic ballet culminating in a new form. This grand slow-motion event is a testament to the ceaseless motion and gravitational sculpting that defines our universe, demonstrating that cosmic change occurs on timescales far beyond human comprehension. The grand movements of galaxies, including the approaching collision of the Milky Way and Andromeda, that will culminate in the birth of Milkdromeda, are not random acts of cosmic fate. They are the intricate outcomes of a fundamental process known as hierarchical structure formation, the universe's preferred method for building its most magnificent structures. Imagine the cosmos not as a static canvas, but as a vast evolving tapestry, woven by the subtle, relentless forces of gravity. In this cosmic tapestry, structure builds from the bottom up, a principle often called bottom-up formation. The very first seeds of structure in the universe were tiny density fluctuations, from the early cosmos barely discernible ripples in the primordial soup of matter and energy. These infinitesimal overdensities, born from quantum fluctuations in the very fabric of space-time, slowly began to attract more matter, over billions of years patiently gathering the diffuse cosmic gas. These initial clumps, often composed primarily of dark matter, eventually grew into the first dwarf galaxies, mere fragments of their future selves, small bundles of stars and gas that represented the universe's earliest attempts at creating complexity. These dwarf galaxies in turn gravitationally attracted each other, merging and coalescing over billions of years to form the larger spiral and elliptical galaxies we observe today, including our own Milky Way and the Andromeda galaxy. This process is continuous, a relentless gravitational dance where smaller entities combine to form larger ones like cosmic building blocks, assembling themselves into ever grander structures. The galactic ballet we discussed earlier, the merger of our galaxy with Andromeda, is just one instance of this ongoing hierarchical process operating on a truly colossal scale. Galaxies themselves are not isolated islands. They're gravitational partners bound together in larger associations. These associations form the next rung on the cosmic ladder, galaxy groups. Our local universe is a testament to this ongoing process, a vibrant cosmic workshop where the very fabric of space-time is continually being sculpted by the invisible hand of gravity, assembling the universe brick by gravitational brick. These groups then fall into even larger structures known as galaxy clusters, which are the largest gravitationally bound structures in the universe. This nested hierarchy from small dark matter halos to immense galaxy clusters means that the universe's structure is fundamentally lumpy, not smooth. This cosmic architect's principle of hierarchical structure formation provides the underlying framework for understanding the distribution of galaxies across the universe, forming the vast cosmic web. It explains why we see galaxies organized into filaments and walls interspersed with immense voids, all sculpted by the relentless attractive power of gravity. It is the fundamental process that drives the unsettling drift of galaxies and culminates in phenomena like the Great Attractor, revealing the profound self-organizing nature of the cosmos itself. This continuous process of accretion and merger is the engine of cosmic evolution, building complexity from simplicity, one gravitational embrace at a time. At the next level of cosmic organization beyond individual galaxies like our Milky Way, which is currently undergoing a galactic bob through the local bubble, we find galaxy groups. Our own Milky Way is a central dominant member of such an assemblage aptly named the local group. This our local neighbourhood is a relatively modest collection, spanning roughly 10 million light-years, defined by the gravitational bonds between its constituent members. It is dominated by two gravitational titans, our Milky Way and the Andromeda galaxy, which we now know is an approaching colossus, destined for a galactic ballet, and the birth of Milkdromeda. Alongside these giants are a handful of other spirals like the triangulum galaxy M33, the third largest member, and a multitude of smaller, fainter dwarf galaxies. These include the large and small Magellanic Clouds, irregular dwarfs that orbit the Milky Way, and other fainter spheroidal dwarfs like the Sculptor Dwarf or Fornax Dwarf, which are galactic satellites and companions orbiting their larger brethren. The local group currently comprises over 50 galaxies, though many of them are small, diffuse and challenging to detect. The local group is not static. It is a gravitationally bound system, meaning that the collective gravitational pull of its members is strong enough to overcome the overall expansion of the universe. It is destined to remain together even as the cosmos expands around it. Unlike larger unbound structures we will discuss later, over unimaginable eons, the individual galaxies within the local group will continue their gravitational dance, pulling and merging with one another, driven by the principles of hierarchical structure formation. The most dramatic event, of course, will be the collision of the Milky Way and Andromeda, culminating in the birth of Milkdromeda approximately 5 billion years from now. But the story of the local group's fate doesn't end there. Over the next 100 billion years, the remaining smaller galaxies within the local group will slowly and inexorably fall into the gravitational embrace of this new mega-galaxy Milkdromeda. The Triangulum galaxy, for instance, is predicted to either collide with Andromeda before or during our merger, or perhaps later be absorbed by Milkdromeda. Milkdromeda will grow, absorbing its cosmic neighbours, consolidating the vast majority of the local group's stellar mass into a single colossal elliptical entity. Our immediate cosmic neighbourhood, the familiar collection of galaxies we see today, is destined to become a single monolithic supergalaxy, a testament to the irresistible power of gravity on galactic scales, forging ever larger structures from the cosmic dust. This ongoing cosmic accretion demonstrates that even within our defined local space, the universe is relentlessly dynamic, always reshaping itself, moving towards a future that is simultaneously grand and profoundly transformative. The cool night air bit at the cheek of Dr. Harris Thorne as he adjusted the focus on the great telescope. Its massive eye pointed towards a faint shimmering smudge in the distant black. For centuries, that smudge known as M87 had been a puzzle, then a marvel, and now, to Harris and his colleagues, it was a profound declaration. It was the heart of something immense, something that orchestrated the movements of galaxies on a scale that dwarfed even the coming embrace of Andromeda. We, the inhabitants of the Milky Way, were not merely drifting. We were being pulled unequivocally by a force both ancient and relentless. The gravitational embrace of the Virgo cluster. Our journey through the cosmos, as revealed across countless chapters, has been one of ever-unfolding motion. We charted the subtle yet powerful peculiar velocities that distinguished our true cosmic drift from the simple expansion of the universe. We understood our Milky Way's own elegant spiral held together by the invisible scaffolding of dark matter. We braced for the inevitable slow-motion impact with Andromeda, a galactic dance foretold. But the universe in its grand design always held more layers, more unseen hands guiding our fate. Beyond the local group, beyond even the vastness of the empty void that often seemed our immediate neighbourhood, lay a gravitational colossus that commanded our attention. The Virgo cluster. For decades, even as we grappled with the elusive Great Attractor, that enigmatic unseen mass drawing our local group and countless others towards it, a more proximate yet still immense gravitational well asserted its dominance. Imagine a celestial cartographer charting not just cities or continents, but entire islands of stars. The Virgo cluster, a sprawling collection of thousands of galaxies, is that super island, the undisputed gravitational centre of our own local supercluster. It lies some 50 million light-years distant, a colossal congregation of stellar cities, each contributing its share to a cumulative gravitational field so vast, so potent, that it shapes the very flow of space-time around it. Our local group, a modest gathering of galactic neighbours, including the Milky Way and Andromeda, is not stationary within this larger cosmic architecture. Now we are in a perpetual stately plunge towards Virgo. This is the Virgo infall, a significant component of our peculiar velocity, a testament to the hierarchical structure formation that weaves the universe into its grand cosmic web. The pull is undeniable, a steady accelerative force that has been shaping our trajectory for billions of years. While the Great Attractor, lying even further beyond Virgo, represents the ultimate destination in our cosmic drift, it is the Virgo cluster that constitutes the most immediate dominant gravitational anchor beyond our local group. It's the closest major nexus in the universe's vast network of mass. Disentangling these gravitational influences has been one of cosmology's most profound challenges. How much of our 600 km per second peculiar velocity is due to Virgo? and how much to the Great Attractor or even larger, more distant superclusters, it's a cosmic riddle that requires immense precision, analysing the motion of thousands of galaxies to map the contours of the local gravitational landscape. It demands a mastery of the cosmic background's whisper, that ancient light carrying the imprint of our true motion, to peel back the layers of influence. The revelation of Virgo's gravitational embrace is another profound twist in our understanding of our place in the cosmos. It reminds us that our galaxy, far from being an isolated island, is intricately connected, a mere cell in the vast living organism of the local supercluster. We are not just speeding towards Andromeda. We are part of a grander current drawn inexorably towards the dense heart of Virgo, pulled by the sheer overwhelming weight of 1,000 billion suns. We are participants in a cosmic dance of unprecedented scale, our home galaxy, merely a leaf on an invisible galactic river flowing towards an unseen yet deeply felt gravitational sea. And the journey as always continues. For millennia, humanity gazed upon the night sky, charting the wanderings of planets and mapping the fixed points of the stars. Our ancestors, from the earliest skywatchers to Copernicus with his daring proposal of a sun-centered cosmos, sought to define our place, to draw the boundaries of our celestial home. But each discovery, from the Earth's own hidden movement to the sun's quiet journey through the Milky Way, only expanded the cosmic frontier, revealing layers of motion currents and drifts previously unimagined. We discovered our galaxy, the Milky Way, was not alone, but part of a local group of galaxies hurtling through space. We traced the gravitational tug of the Virgo cluster, a massive collection that promised to pull us into its dense core. But even this grand structure, the Virgo supercluster, was merely a signpost pointing to something far vaster. Imagine standing on a mountaintop surveying an immense river basin. You see the main river fed by countless tributaries, all flowing inexorably towards a singular unseen delta. Each stream, each brook, each raindrop falling on the highest peak contributes to this grand hydrological cycle, united by gravity's relentless pull. This is not unlike the universe on its grandest scales. For decades, the enigma of the Great Attractor, that mysterious unseen hand pulling our local group and the entire Virgo supercluster towards it, remained a gravitational ghost, a force without a fully mapped form. It was a signpost, yes, but to what? The answer, when it finally emerged, was a revelation born from the tireless efforts of astronomers, using the very peculiar velocities we had come to understand as our cosmic compass. Just as the cosmic background's whisper had revealed our galaxy's drift, so too could the subtle non-Hubble flow movements of thousands of galaxies map the true contours of the universe's largest gravitational structures. Researchers, notably Brent Tully, a modern-day pioneer following in the footsteps of his own earlier work with Fischer, painstakingly charted the gravitational streams, the galactic currents, the cosmic ballet of millions of galaxies. They were mapping the cosmic equivalent of that immense river basin. What they unveiled was Laniakea, a name of Hawaiian origin profoundly meaning immense heaven. This was not just a cluster, nor even a supercluster in the traditional sense of a mere collection of galaxies. Laniakea is defined by flow. It is a vast interconnected network of over 100,000 galaxies stretching 500 million light-years across. Our local group with the Milky Way and Andromeda poised for their inevitable embrace is merely a tiny peripheral tributary within this colossal cosmic river. The Virgo cluster, which once seemed like our ultimate gravitational destiny, is merely a suburb within Laniakea itself, being drawn along with us. At the heart of Laniakea lies the mysterious pull, the true heart of the Great Attractor, a sprawling gravitational minimum that orchestrates the flow of every galaxy within its domain. Imagine a vast shallow bowl where all the water on its surface slowly, patiently drains towards the lowest point. Every galaxy within Laniakea, from the colossal Coma cluster to the relatively humble local group, is gravitationally bound, its peculiar velocity tracing a path inwards towards this shared gravitational well. Our own unseen journey, previously quantified as a drift towards some unknown gravitational force, now had a destination, a grander context. We are not just drifting. We are flowing alongside tens of thousands of other galaxies on a cosmic current. The discovery of Laniakea was a triumph of observation, an unmasking of the giant leveraging the painstaking measurements of peculiar velocities across vast cosmic distances, often peering through the very zone of avoidance that had historically blinded us to the universe beyond our galactic plane. It showed that the universe is not just a collection of islands in a void, but an interconnected web where gravity, the embrace of gravity as unveiled by Newton and deepened by Einstein's relative dance, dictates every grand movement. What awaits Laniakea, this immense heaven we call home, unlike smaller clusters that might one day merge into singular giant elliptical galaxies, the sheer scale of Laniakea means its fate is uncertain. While its internal components flow towards a common centre, the accelerating expansion of the universe driven by dark energy works to tear apart larger structures. Laniakea then exists at a delicate balance, a testament to gravity's organising power on supercluster scales, but perhaps still at the mercy of the cosmos's ultimate expansion. And so we arrive at our truest cosmic address yet. Earth within the solar system in the Milky Way galaxy, which is part of the local group itself, a member of the Virgo supercluster, all flowing within the immense gravitationally bound structure known as Laniakea, from a tiny speck of dust to an integral part of an immense heaven. Our understanding of home has expanded with every passing epoch, each revelation a profound testament to the intricate interconnected dance of the cosmos. We are not static nor alone. We are part of a ceaseless, majestic flow, eternally on a journey through the vast, unfolding universe. The initial whispers of our galaxy's motion, the unsettling drift that stirred our cosmic neighbourhood, came from the faint temperature bias in the cosmic microwave background, CMB, a pattern known as the CMB dipole. This dipole, a slightly hotter region in one direction and a slightly cooler region in the opposite, is a direct imprint of our solar system's movement relative to the most ancient light in the universe. It indicated a colossal velocity approximately 600 kilometers per second. This was the first and perhaps most fundamental piece of evidence confirming the drift on the largest possible scale. The CMB itself is a relic of the Big Bang, a cosmic snapshot from just 380,000 years after the universe's birth, when it cooled enough for atoms to form and light to travel freely. This background radiation is remarkably uniform across the sky, varying by only about 1 part in 100,000. This exquisite uniformity is a testament to the early universe's smoothness, a critical piece of evidence supporting the standard cosmological model. Yet superimposed on this uniformity is the larger scale dipole, a small but significant deviation. This temperature difference a mere 0.0035 Kelvin hotter in the direction of the constellation. Leo and cooler towards Aquarius is a consequence of the Doppler effect. As our solar system rushes through this cosmic sea of photons, the light waves in our direction of travel are compressed, appearing hotter and bluer, while those from behind are stretched, appearing cooler and redder. This 600 kilometers measurement represents our total velocity through the universe's ultimate reference frame, the cosmic background itself. But this was merely our local motion, a composite of various influences. To understand the true flow of our galaxy, the inherent peculiar velocity of the Milky Way independent of our Sun and Earth, we needed to subtract the smaller known motions. This involved accounting for the Earth's rotation, its orbit around the Sun at 30 kbms and the Sun's own majestic 230 journey around the galactic centre, the Milky Way's whirl driven by dark matter. Once these local effects were meticulously accounted for, a substantial residual velocity of about 300 km per second remained. This residual motion pointed unequivocally towards the same cosmic destination, identified by galactic surveys like those pioneered by Tully and Fischer. The Great Attractor and the larger structures within Laniakea's embrace which pull on the clusters like Virgo, the CMB dipole provided a powerful independent verification of these galactic flow measurements, solidifying the evidence for a vast unseen gravitational anomaly. The exquisite uniformity of the CMB, famously smooth at 1 part in a million, only served to highlight the significance of this subtle dipole. It was the universe's fundamental baseline, and our movement against it was a powerful independent confirmation of the large-scale gravitational currents that sweep through the cosmos. The CMB, the echo of creation itself, served as the ultimate cosmic speedometer, painting an undeniable picture of our galaxy's restless journey, and hinting at the unseen gravitational leviathan orchestrating it all. This dipole's fingerprint was the definitive cosmic proof of our galaxy's motion. The Great Attractor, the immense gravitational anomaly pulling our Laniakea supercluster into its vast embrace, as confirmed by both galactic surveys and the dipole's fingerprint in the cosmic microwave background, was famously shrouded by the Milky Way's dense veil, the zone of avoidance. This cosmic blind spot made direct observation incredibly challenging, forcing astronomers to infer its existence solely from the motions of galaxies around it. Yet the persistent pull and the telltale CMB dipole demanded that something immense reside behind that galactic curtain. The problem was clear: how to peer through the veil of our own galaxy's dust and gas to reveal the nature of this unseen hand. The breakthrough came through instruments that could see beyond the visible light spectrum wavelengths, that were not as easily scattered or absorbed by interstellar dust. Radio telescopes, which can penetrate the dust lanes of our galaxy, provided the first crucial glimpses. Later, infrared and X-ray observatories capable of detecting light at wavelengths thousands of times longer or shorter than visible light began to offer tantalizing views into this previously obscured region. These new eyes on the cosmos allowed astronomers to effectively bypass the cosmic blind spot of the zone of avoidance. What these instruments revealed was the Norma cluster, a sprawling collection of galaxies far larger and more massive than typical clusters, located approximately 220 million light-years away, squarely within the previously impenetrable zone of avoidance. Norma presented itself as a formidable gravitational well, a significant component of what we call the Great Attractor. Its sheer density, measured by the number of galaxies packed into its volume, and the immense amounts of hot X-ray emitting gas permeating its intergalactic space, confirmed it as a powerful cosmic engine capable of exerting a considerable gravitational influence on our local group and the broader Laniakea supercluster. The X-ray emission in particular comes from gas heated to millions of degrees by the cluster's intense gravitational potential, making it a bright beacon in the X-ray sky. This was Norma cluster's shadow being cast upon our understanding. However, even with these clearer views, the Norma cluster alone appeared insufficient to fully account for the colossal gravitational pull observed on our supercluster and the full 600 kA motion against the CMB. Its calculated mass, while immense, couldn't explain the entirety of the observed peculiar velocity. This gravitational deficit hinted at an even larger, more distant structure, a true leviathan that lay beyond Norma, extending its invisible tendrils across hundreds of millions of light-years. The mystery, it seemed, only deepened with each new layer of understanding. The discovery of Norma was a crucial step, solving the immediate problem of finding a major component of the Great Attractor, but it simultaneously unveiled a deeper problem. The true scale and ultimate source of the Great Attractor's power remained elusive, prompting astronomers to look even further into the cosmic depths. For decades, the invisible hand guiding our galaxy, the mighty Great Attractor, remained an enigma wrapped in a cosmic riddle. We had pieced together fragments like ancient archaeologists unearthing a colossal buried city. Chapter by chapter, the story unfolded. First, the very idea of our Milky Way not being static but rushing through the void, a profound revelation after millennia of believing in an unmoving Earth. Then the realization of a colossal gravitational tug drawing us inexorably towards a cosmic unknown. Norma the cluster, veiled in dust, emerged as a significant component, a powerful arm of this unseen force, its shadow cast across our celestial vision. But even Norma, immense as it was, could not fully account for the observed pull. There was a residual, a whisper of something vaster, a deeper shadow cast across the cosmic canvas. The universe, it seemed, still held a secret, a missing piece in the grand puzzle of our cosmic drift. This was the essence of the simplicity versus complexity paradox at play, the clear decisive signal of the cosmic microwave background dipole, that unmistakable fingerprint of our motion, pointed to an incredible speed, yet the gravitational sources we had identified were not quite enough to explain it. We were seeing the effect, but not yet the full cause. The answer, it turned out, lay even further afield, deeper still within that cosmic blind spot, the very zone of avoidance that had long obscured our view of the universe's most dramatic structures. It was a place of celestial silence where the dust and gas of our own galactic plane smothered the light from distant realms. Yet it was precisely within this zone of avoidance, this cosmic curtain, that the true orchestrator of our galactic destiny lay hidden, cloaked by the very fabric of our home galaxy. Imagine a team of cosmic cartographers much like Commander Elias Thorne and Dr. Anya Sharma of the Starship Odyssey, diligently mapping uncharted nebulae only to find a vast, dark, impossible structure beyond the known edge. For years, this region was a blank on their maps, a terrifying void, but with persistence and new instruments capable of piercing through the obscuring veil of interstellar dust, they began to glimpse something colossal. It was not a single isolated giant, but an immense concentration of matter, a sprawling interconnected network of galaxy clusters and filaments, far grander than anything previously imagined. This was the Shapley supercluster, named for the pioneering astronomer Harlow Shapley, whose early 20th century maps of globular clusters laid foundational groundwork for understanding our galaxy's place in the universe, albeit on a different scale. What better namesake for a structure so profound, so influential, yet for so long merely a shadow? Shapley himself, in his tireless quest to map the cosmos, would have been awestruck by this gargantuan structure. The Shapley supercluster, a titanic collection of thousands of galaxy clusters, each containing hundreds, even thousands of individual galaxies, dwarfed even the Laniakea supercluster, of which our local group is merely a peripheral tendril. It was the veritable cosmic mountain towards which our entire local cosmic neighbourhood, the vast Laniakea supercluster, was being drawn. Its immense gravitational potential finally provided the missing piece of the puzzle, accounting for the full extent of the Great Attractor's influence, and thus for the precise measurement of our Milky Way's peculiar velocity, that monumental drift of 600 kilometers per second. This was the ultimate source of the dipole's fingerprint, the final anchor of that cosmic current revealing the true scale of the cosmic ballet. This was no isolated anomaly, but a nexus of gravitational power, a density peak so immense it pulled everything in its vicinity, including our own supercluster, into its inexorable flow. The Great Attractor was not a single pinpoint object, but a complex distributed region of gravitational influence, a landscape of cosmic valleys and peaks, with Shapley as its deepest chasm. We, along with Andromeda, Virgo, and countless other galaxies within Laniakea, are but leaves upon a vast unseen current, all pulled by the gargantuan gravitational well of Shapley. It is the cosmic equivalent of a gravitational mountain range, pulling everything downhill towards its peak. The discovery of Shapley lurking in the shadows of the zone of avoidance was a profound testament to humanity's unyielding drive to map the unknown. It turned a perceived void into a beacon, a once empty space into the gravitational heart of a vast cosmic flow. It reinforced the majestic narrative of hierarchical structure formation, where smaller structures coalesce into larger ones, culminating in these superclusters that dictate the grand cosmic dance. We are not just drifting. We are part of an unimaginably vast interconnected system drawn by the invisible threads of gravity towards a centre beyond our immediate view. The universe in its elegant complexity continues to reveal its secrets, one cosmic shadow at a time, each revelation deepening our sense of awe for the grand design and forever changing our address in the cosmic tapestry. Our understanding of the universe's large-scale structure and the forces that shape its movements, including the unsettling drift of our Milky Way and the pull of the Great Attractor and Shapley's shadow, relies heavily on faint echoes from the cosmic dawn. One of the most powerful of these echoes are baryon acoustic oscillations, or BAOs. Imagine the early universe a mere 380,000 years after the Big Bang as a hot, dense soup of plasma, a superheated, opaque mixture of protons, electrons, and photons. Within this soup, gravity was already at work trying to pull matter together, forming initial overdensities while the immense pressure from the trapped photons pushed it apart, acting as a counteracting force. This cosmic tug-of-war created pressure waves like sound waves propagating through water outward from these initial overdensities. These galaxy-dwarfing sound waves rippled through the primordial plasma pushing matter outwards in expanding spherical shells. The baryons, or normal matter protons and electrons, were dragged along by the photons, forming a coupled fluid. As these waves expanded, they left behind slight overdensities of matter at the crest of each wave, akin to ripples on a pond freezing at a specific moment. Then, at about 380,000 years after the Big Bang, a critical event occurred. The universe cooled enough for electrons and protons to combine, forming neutral atoms. This event, known as recombination, freed the photons, allowing them to stream freely through space. These newly liberated photons formed the cosmic microwave background CMB, which we observe today as the dipole's fingerprint that helps confirm our galactic drift. Crucially, the instant the photons decoupled from the baryons, the photon pressure that had been pushing matter outwards abruptly ceased. The sound waves effectively froze in place, leaving behind a persistent imprint in the distribution of matter, slight overdensities of baryons at a characteristic distance, a standard ruler stretching across the cosmos. These frozen ripples, these fossilized sound waves, manifest today as a statistical bump in galaxy separation, indicating a preferred distance of about 150 megaparsecs, or approximately 490 million light-years between galaxies. This preferred separation is a direct relic of the size of the sound horizon at the time of recombination. Astronomers use these baryon acoustic oscillations as powerful tools for cosmic forensics. By measuring this characteristic scale in the large-scale distribution of galaxies, they can accurately determine cosmic distances and precisely track the history of the universe's expansion. They provide a direct window into the time before the CMB, when the universe was truly a noisy place. A dense hot plasma throbbing with primordial sound waves. The baryons are a key piece of evidence for the standard cosmological model, and are indispensable for mapping the cosmic web and understanding the underlying gravitational forces, like those responsible for the pull of the clusters and the unsettling drift of our galaxy. They reveal how the universe's largest structures are not randomly distributed, but bear the ancient subtle imprint of its earliest moments. The fossilized sound waves of baryon acoustic oscillations, those frozen ripples from the early universe, are not just theoretical constructs. They are detectable patterns etched into the distribution of galaxies across the universe, providing a cosmic ruler for understanding large-scale structure. In 2023, building on his pioneering work with the Cosmic Flows project that helped define Laniakea's embrace R, Brent Tully made another profound discovery related to these ancient ripples. He identified Huolelana, a colossal spherical shell of galaxies approximately 400 to 500 million light-years in diameter, encompassing some of the most prominent large-scale structures we know, including the Sloan Great Wall. The name Huolelana comes from Hawaiian mythology, meaning murmurs of awakening, a fitting tribute to the faint echoes of the universe's beginning embedded in the very fabric of its structure. This discovery further solidifies our understanding of how structure formed and evolved from the early cosmic soup. Huolelana represents a significant confirmation of the Bayo scale. Its central void, a region of remarkably low galaxy density, is surrounded by a shell of galaxies, a direct imprint of those primordial sound waves that propagated through the early universe. This finding gives us a deeper insight into how matter clustered and distributed itself over cosmic time, forming the vast cosmic web of filaments and voids. It's a remarkable piece of cosmic forensics, allowing us to trace the universe's development from its very infancy to the present day. But the universe's large-scale structure is not just about gravitational pulls like those exerted by the Great Attractor and Shapley's shadow. It's also about pushes. Alongside the colossal superclusters and galaxy filaments, there are vast and nearly empty regions known as cosmic voids. These immense bubbles of emptiness are not just passive gaps where gravity has simply failed to pull matter together. They are active participants in shaping the cosmic web. While gravity pulls matter towards denser regions, the less dense voids expand faster than the universe as a whole, effectively pushing galaxies away from their centers. This creates a powerful outward pressure that contributes to the motions of galaxies around them. An excellent example of this is the dipole repeller, a cosmic void discovered in 2017. This colossal void, stretching for hundreds of millions of light-years, is located on the opposite side of our galaxy from the Great Attractor. In concert with the gravitational pulls from the Great Attractor and the Shapley supercluster, The dipole repeller's repulsive force helps explain the full magnitude of our local group's peculiar motion, including the unsettling drift of our Milky Way. These cosmic voids, once seen as mere absences of matter, are now understood to be dynamic components of the universe, their outward pressure counteracting the inward pulls of gravity, creating a delicate balance that shapes the ever-evolving architecture of the cosmos. The universe is a constantly breathing entity, expanding in some places, contracting in others, forever in flux driven by both attraction and repulsion, revealing the murmurs of awakening in its grand structure. The soft glow of a desk lamp cast long shadows across the stacks of crumpled paper. Albert Einstein, his brow furrowed in concentration, stared at the equations sprawled across a blackboard. It was the year 1917, and his revolutionary general theory of relativity had just reshaped humanity's understanding of gravity and space-time. But a new problem gnawed at him. His elegant equations, when applied to the universe as a whole, suggested something profoundly unsettling. The cosmos could not be static. It must either expand or contract. Yet the prevailing wisdom, the very bedrock of astronomical thought since the dawn of observation, held that the universe was unchanging, eternal. The stars, the galaxies, they were fixed beacons in an infinite, unmoving cosmos. How could his pristine mathematics defy such a deeply ingrained truth? With a sigh, Einstein introduced a new term into his field equations, a small, seemingly innocuous value. He called it the cosmological constant. Its purpose was simple: to act as a repulsive force precisely counteracting gravity's pull, thereby ensuring a perfectly balanced static universe. It was a patch and addendum, a mathematical concession to what he believed to be the universe's immutable reality. Later, he would famously lament this addition, calling it his biggest blunder. A decade later, the universe began to whisper secrets that would shatter the illusion of stasis. In Chapter 18, we witnessed Edwin Hubble's groundbreaking discovery that the Andromeda Nebula was in fact an island universe, a galaxy unto itself. But Hubble's relentless observation, coupled with the work of Vesto Slipher and others, revealed an even more profound truth. The universe was not static. The vast majority of galaxies were rushing away from us, and the farther they were, the faster they receded. The cosmos was expanding, just as Einstein's original equations had hinted. With the empirical evidence of an expanding universe undeniable, the cosmological constant seemed redundant, an unnecessary crutch for a static cosmology. Einstein, humbled by the universe's unexpected dynamism, cast it aside, believing it to be a theoretical misstep. It was a testament to his intellectual integrity, yet it also highlighted how even the greatest minds can be tethered by the prevailing paradigms of their era. The elegant simplicity of an expanding cosmos unburdened by an artificial counterforce seemed triumphant. For decades, the constant lay dormant in the annals of physics, a relic of a discarded notion. Then, at the close of the 20th century, the universe threw another curveball. Teams of astronomers, including the High-Z Supernova Search Team and the Supernova Cosmology Project, were meticulously observing distant Type Ia supernovae, cosmic lighthouses whose predictable brightness allowed them to serve as cosmic distance markers. Their mission was to precisely measure the universe's expansion rate and determine if it was slowing down due to the gravity of all its matter. What they found was utterly astonishing. The expansion wasn't slowing, it was accelerating. The distant supernovae were fainter than expected, implying they were farther away than their redshift alone suggested. This meant the universe's expansion was speeding up. It was as if, after the initial outward burst of the Big Bang, some unseen force was pushing the fabric of space-time apart, accelerating its cosmic drift. The universe, it seemed, was not content to simply expand. It was being driven by a mysterious, pervasive energy, a cosmic anti-gravity. And what was the simplest, most elegant way to describe this pervasive, repulsive force within the framework of general relativity? Einstein's discarded cosmological constant. It had returned, redeemed not as a force to maintain stasis, but as the mathematical embodiment of what we now call dark energy, the enigmatic dominant component of our cosmos responsible for its accelerating expansion. From a perceived blunder, a mathematical fix to conform to a mistaken belief, it had morphed into the best explanation for the universe's most startling behaviour. The simplicity of a single constant, once an embarrassing footnote, had become the profound explanation for the cosmos's greatest riddle, illustrating the simplicity versus complexity paradox. The universe in its grand cosmic ballet had not only proven Einstein right in his initial prediction of expansion, but had also decades later resurrected his blunder as its defining characteristic. The journey of cosmic discovery, like the universe itself, is full of unexpected turns, where yesterday's errors can become tomorrow's revelations, pushing the boundaries of human comprehension ever outward into the vast accelerating unknown. Imagine for a moment a cosmic ship, the stellar nova, adrift in the deep intergalactic void. Its engines are silent, long since spent. Its sole purpose, according to Captain Eleanor Vance, was to drift to measure the subtle currents of the cosmos as the universe gently slowed its expansion. For eons, it had been a common assumption among the starfarers. After the initial explosive push of the Big Bang, the mutual gravitational embrace of all matter must inevitably slow everything down, like a stone thrown skyward eventually succumbing to Earth's pull. Eleanor, gazing at the distant ancient galaxies through her holographic viewer, expected to see them gradually, infinitesimally drawing closer together, or at least decelerating their flight from one another. But the data flowing from stellar nova's instruments meticulously collected over centuries told a different story. It was a story so audacious, so contrary to every ingrained intuition about the cosmos, that it initially drove Eleanor and her predecessors to question their very sanity. Instead of slowing, the distant galaxies were accelerating away. The cosmic fabric itself wasn't merely expanding, it was stretching at an ever-increasing pace, as if an invisible, inexhaustible force was constantly pulling on its seams. This was the cosmic revelation that rocked the scientific community at the close of the 20th century, echoing the profound shifts brought by Copernicus, Newton and Einstein. For centuries, our understanding of the universe's ultimate fate had been a cosmic tug-of-war. On one side, the colossal momentum of the Big Bang pushing everything outward. On the other, the relentless seductive embrace of gravity working to pull it all back together to condense perhaps into a fiery big crunch. We had meticulously mapped our own journey, a peculiar velocity that saw our Milky Way galaxy propelled by the unseen hand of the Great Attractor, and the vast embrace of Laniakea hurtling through the local flow. We had even confirmed the cosmic dipole's fingerprint, testifying to our unseen drift. But this new discovery wasn't about our local motion. It was about the very texture of space-time itself across the entire observable universe. The first whispers of this extraordinary truth came not from the direct observations of galactic motions within our local group, nor from the gravitational influence of familiar clusters like Virgo or Shapley's Norma cluster. Instead, they emerge from the faint, distant gleam of Type Ia supernovae, cosmic lighthouses whose predictable brightness allowed astronomers to measure their distances with incredible precision. When comparing these distances to the redshift of their host galaxies, the universe was revealed to be dimmer and thus farther away than expected for its age, implying an acceleration of its expansion. This was the ultimate scientific twist, turning everything we thought we knew about the universe's destiny on its head. What could possibly be responsible for such a cosmic push and anti-gravitational force arising from the very fabric of existence? The answer startlingly lay in the vacuum itself. The empty space, once thought to be nothingness, was revealed to be a reservoir of hidden power, a latent energy that pushed space apart. We call it dark energy. It's a paradox that resonates with the motif of simplicity versus complexity. How could the void, the ultimate emptiness, possess such profound might? Yet like the elusive dark matter that sculpts the Milky Way's whirl, or the vast empty cosmic voids like Ho'olilana dark energy, is another testament to the universe's hidden depths. It's not matter, nor is it radiation. It behaves differently. Its density remains constant even as space expands. As the universe grows larger, the amount of dark energy increases because there's simply more vacuum. This makes it fundamentally different from matter and radiation, which dilute as space expands. In the early universe, when everything was crammed together, matter and radiation dominated their gravitational pull, slowing the expansion. But as the universe swelled, matter and radiation became increasingly diluted, their influence waning. Dark energy, however, did not dilute. It maintained its constant pressure, an inherent property of space itself. At some critical point in cosmic history, roughly 5 billion years ago, dark energy finally became the dominant force, overcoming the slowing grip of gravity and ushering in an era of accelerating expansion. This cosmic dominance of dark energy has profound implications for the universe's future. The Andromeda galaxy is still on an inevitable embrace, with our Milky Way creating Milkdromeda, but beyond our local gravitationally bound group, the rest of the cosmos is destined to become increasingly isolated. Distant galaxies will recede faster and faster, eventually vanishing beyond the cosmic horizon, their light unable to reach us as the space between us stretches at superluminal speeds. The cosmic dance, foretold the grand ballet of clusters forming hierarchical structures, will continue locally, but the grander universal story will be one of increasing emptiness and isolation. And so Einstein's blunder, his cosmological constant originally introduced a force, a static universe, then famously regretted, was spectacularly redeemed, not as a force for stasis, but as the very engine of cosmic acceleration, a testament to the universe's astonishing ability to surprise us. This vacuum's hidden power, this omnipresent repulsive force, constitutes roughly 68% of the entire universe's energy density, making it the most significant yet least understood component of our cosmic inventory. We embarked on this journey exploring the unseen drifts and pulls, discovering the Great Attractor and Laniakea, but nothing prepared us for the revelation that the very emptiness of space holds the key to the universe's ultimate destiny. The vacuum, it turns out, is anything but empty. The accelerating expansion driven by dark energy, the vacuum's hidden power, has profound implications for the universe's large-scale structure, reshaping its grand architecture in ways that defy our intuitive understanding of gravity's dominance. While gravitationally bound structures like galaxies, which have undergone processes like the Milky Way's whirl, and will face the approaching colossus to form Milkdromeda galaxy groups such as our local neighbourhood, and galaxy clusters like Virgo's gravitational embrace will remain intact, their internal gravitational pull strong enough to overcome the expansion, the looser affiliations of superclusters are doomed. This marks the unravelling cosmos, the vast, nearly empty regions known as cosmic voids, which are now understood to be active components. Cosmic voids, in the murmurs of awakening, are expanding at an even faster rate than the denser filaments of the cosmic web. As dark energy continues to dominate, these voids will merge, swallowing the smaller pockets of denser matter and expanding relentlessly. This means that superclusters like our Laniakea's embrace, which are not gravitationally bound but rather defined by the collective flow of their member galaxies towards a Great Attractor, or Shapley's shadow, will eventually be torn apart. The gravitational threads that currently connect them, remnants of Baryon acoustic oscillations and cosmic architects at work, will stretch and break as the accelerating expansion pushes their constituent galaxies further and further apart. The universe, which once resembled a vast interconnected sponge with filaments of galaxies surrounding immense voids, will begin to unravel. The cosmic web, once a cohesive network of galactic superhighways, will fray its threads, snapping as the space between galaxies grows exponentially. This is a slow, inexorable process, a gradual isolation where only the most tightly bound gravitational islands will survive. Imagine a vast, intricate lace fabric being stretched without limit. Eventually, the delicate connections between its patterns will rupture, leaving only isolated, self-contained islands of thread. This future scenario stands in stark contrast to the earlier universe, when gravity reigned supreme, continually building larger structures through hierarchical structure formation. Now, dark energy dictates a different fate. Galaxies not already bound within clusters or groups will drift away from each other, eventually becoming unobservable to any future inhabitants of an isolated galaxy like Milkdromeda. The cosmic horizon, the boundary beyond which light cannot reach us due to the accelerating expansion, will shrink, progressively erasing distant galaxies from our view. It's a profound shift from a universe of constant interaction and growth to one of ultimate isolation. This gradual dissolution of large-scale structure is a testament to the triumphant, albeit unsettling power of the vacuum's hidden energy, slowly transforming the vibrant interconnected cosmos into a fragmented, lonely expanse where voids merge, superclusters dissolve. This means the majestic journey of our galaxy toward the Great Attractor will never be completed. The accelerating expansion driven by dark energy, the vacuum's hidden power, will ultimately transform the observable universe into a landscape of profound isolation. This relentless repulsive force, which caused the unraveling cosmos by making voids merge and superclusters dissolve, also dictates a grim future for the visibility of distant galaxies. Our Milky Way, even after its majestic merger with Andromeda to form Milkdromeda, will never reach the Great Attractor, nor the Shapley supercluster, nor any other distant cosmic giant. The space between our local mega-galaxy and these distant structures will expand faster than their gravitational pull can overcome. Imagine a ship on a vast accelerating current. No matter how fast it sails, it can never reach a distant port if the current is pulling the port away faster than the ship can travel. So it is with cosmic structures not already gravitationally bound to our local group. Over trillions of years, galaxies beyond our immediate cosmic neighborhood will recede faster and faster, their light stretched to increasingly longer redder wavelengths by the expanding space. This extreme redshift will eventually shift their light out of our observable spectrum, entirely rendering them invisible. Each distant galaxy will simply wink out, becoming an unseeable memory, lost to the accelerating expansion, a phenomenon known as the fading light. From the perspective of any future civilization residing in Milkdromeda, the night sky will become an increasingly barren canvas, devoid of the countless galaxies we can observe today. The cosmic horizon, the boundary beyond which light cannot reach us due to the accelerating expansion, will continually shrink. This means that an ever-decreasing portion of the universe will be visible as galaxies cross this horizon and their light becomes forever out of reach. This gradual disappearance of the cosmos beyond our local cluster represents a profound cosmic isolation. The universe once a vibrant, interconnected cosmic web will become a collection of isolated islands of matter, each one a gravitationally bound entity separated by vast, dark, ever-expanding voids. The light from distant superclusters, once bright beacons, will fade into an impenetrable cosmic loneliness. This means that future astronomers in Milkdromeda billions of years from now will have no way of observing other galaxies beyond their immediate local group. They will be unable to study the cosmic background's whisper, or witness the unsettling drift of other galaxies, or discover their own Great Attractor, because the evidence will have expanded beyond their reach. The empirical data that we rely on today to understand the Big Bang and the large-scale structure of the universe will become utterly inaccessible. This future is not one of dramatic collapse or grand collision for the vast majority of structures, but a slow, quiet fade into an unimaginable, eternal cosmic solitude. The boundless ocean of galaxies, so vividly unmasked by Hubble, will recede into an ultimate, unobservable darkness. Imagine an epoch so far removed from our own, it renders the very concept of time a quaint historical curiosity. Picture a sentinel, perhaps a solitary bioengineered consciousness, adrift on a long-dead world, its star a cinder, its galaxy a phantom. For eons, this entity, let us call it Ethel, has watched the last embers die, the final photons stretch into oblivion. The vibrant, bustling cosmic canvas we know has long since faded. In the time of Ethel, the relentless accelerating expansion of the cosmos propelled by dark energy's relentless whisper, a whisper now a roar, has utterly reshaped reality. The grand cosmic dance, the stately waltz of Laniakea toward Shapley's embrace, the Milky Way's inevitable collision with Andromeda. These were but fleeting moments, vibrant but ultimately ephemeral blips in a saga of inevitable dissipation. We spoke of our own unseen journey, the dipole's fingerprint etched upon the cosmic microwave background, revealing our peculiar velocity, a rush of 620 kilometers per second, a galactic sprinter in a vast cosmic marathon drawn by the Great Attractor, the collective gravitational might of Virgo and Norma cluster, and the grander gravitational currents of Shapley's shadow. Our very existence was defined by motion, by the cosmic eddies that shape structures from primordial gas, the concept of motion, which has been the beating heart of our cosmic journey from the galaxy adrift to the cosmic dipole's fingerprint, finds its ultimate antithesis in the universe's final act. But what happens when the very fabric of space stretches so relentlessly that gravity, the cosmic architect that built hierarchical structure formation, is finally overwhelmed? What happens when the distances between galaxies become so vast, so insurmountable, that even the closest neighbours recede beyond sight, beyond communication, beyond even the reach of light? This is the unravelling cosmos we began to foresee. The voids merge, consuming the superclusters. The filaments dissolve. What were once the cosmic fossils of Baryon acoustic oscillations, frozen ripples in the early universe, are now stretched to invisible attenuation. The universe doesn't end with a bang, nor truly with a whimper, but with an exhale, a slow, inexorable sigh of isolation. Our local group, perhaps even Milkdromeda, might remain gravitationally bound, a tiny island in an ocean of ever-expanding nothingness. But beyond our immediate cosmic neighbourhood, every other galaxy, every cluster, every luminous point of light will recede into an infinite, unreachable distance. Their light, once a testament to their vibrant existence, will be redshifted into oblivion, becoming waves too long, too faint to ever register. The peculiar velocities that once defined our motion become meaningless. There is no there to move towards, for there has receded beyond comprehension. The very concept of drift, our cosmic imperative, evaporates. The universe itself approaches a state of ultimate stillness, a pervasive chilling uniformity. All motion, all the dynamic interactions, all the grand gravitational ballets slow, then cease, or continue in utter isolation beyond the reach of any observation. Stars like Sol eventually exhaust their fuel, turning into white dwarfs, then black dwarfs. The great galactic whirls of dark matter will continue their internal dance, but as the eons pass, even they will decay matter. Evaporating protons, decaying black holes, consuming and eventually evaporating through Hawking radiation. The universe descends into a state of maximum entropy. The fading light yields to an eternal night. This is the universe's final whisper, not a roar of a new beginning, not the vibrant hum of ongoing creation, but the soft, chilling breath of an ultimate equilibrium. A time when all energy is uniformly distributed, when no temperature differences drive any process, when motion, in any meaningful, observable sense, has yielded to an all-encompassing stillness. The grand narrative of the cosmos, from the chaotic birth to the dynamic Middle Age, culminates not in fiery apocalypse, but in an infinite cold, empty silence. And so we, the ephemeral observers perched on our pale blue dot, find ourselves in a remarkably privileged moment. We exist in the universe's vibrant middle act, a cosmic spring before the long winter. We are the generation, the species, the brief flicker of consciousness uniquely positioned to witness the cosmic ballet in its full majestic glory, to measure its drifts, to chart its collisions, to feel the pull of its great attractors, to understand that our fleeting motion, so significant to us, is but a fleeting prelude to an infinite stillness. The universe whispered its beginning with the Big Bang, and it will whisper its end not with a final dramatic gasp, but with an eternal cold silence, where even the memory of motion is lost, and the grand cosmic dance gives way to an ultimate profound stillness. Thank you for watching Astro Horizons. We hope you found this exploration insightful and engaging. If you enjoyed this journey with us, please give this video a like and share it with others who might find it interesting. Don't forget to subscribe to Astro Horizons and hit the notification bell so you stay updated on all our future cosmic adventures. We look forward to seeing you in the next one.